Folks, we're going to talk about some two-object interactions, and specifically later we're going to look at motion and momentum of objects relative to what we call the center of mass reference frame. And we'll talk specifically about why that's important and helpful for a certain kind of problem. So we're going to talk a bunch about center of mass here, and we'll start with a definition of where this system's center of mass is at this initial instant. All right, initially we have these two masses a distance 2d apart. Mass 3m is moving at speed v to the right. Mass little m is stationary. By definition, the position of the center of mass is the sum of all the position and mass products divided by the sum of all the masses. So we have to define where we're measuring from, and let's measure from here. So the product of the position of the 3m mass and its mass, well, the position of this 3m mass relative to our origin is 0, so that term drops out. And what we do have is this mass at position 2d. So that's all we get is 2dm over the sum of all the masses, 4m. So that position is 2d over 4, or d over 2, as measured relative to here. Well, here's d, here's d over 2. And yeah, that makes sense. The center of mass is 3 times closer to the object that's 3 times as massive. You dig? Okay, so this is a distance d over 2. Now, later, after some amount of time t, here's some final instant, we do the same operation. Position of center of mass is same expression. Now, let's see, why don't we still measure from here? Okay, and we get 3m locate, so we get at position D, we get 3m, and then at position 2D, we get m over 4m. We've got a common m factor in all those, so that's 5d over 4. All right, 5d over 4 is a quarter past, so if this is a d, there's a half a d, there's a quarter of d, and yeah, once again, this is a quarter d, and this is 3/4 d, so yeah, the position of the center of mass is 3 times closer to the object that's 3 times as massive. Makes sense. Now, this center of mass has moved from here to here, right? From here to here in some amount of time t. So we can talk about the velocity of the center of mass. And that's the change in position of center of mass divided by some amount of time. Well, we went from half d to 5/4 d, so that's a half and a quarter it's moved. So that's 3/4 d, 3d over 4 in time t. Yeah? Or we could call that, if we want, 3d over 4t. Okay? Now, if these masses were to hit and stick, here's what we could say. If we apply momentum conservation, well, we say that all the initial momentum and all the final momentum are the same thing. Well, in the beginning, all we have is 3m moving at speed v. This object is not moving, thus no momentum. If they hit and stick, what they do is, at the end, the two of them move at some final velocity. Right? So what we get is 3mv. We get that v final is 3mv over 4m, or the final speed of this system will be 3/4 of that initial velocity. Oh, look, we said that the speed or velocity of the center of mass is 3/4 d over t. But look, d over t is how far this object moved in that amount of time. Well, that's this speed v. So VCM is 3/4 v. If these things were to hit and stick, their final speed as a system would be 3/4 v. So this says that the center of mass. Now, if these things hit and stick, their center of mass is where both objects are. Now we have to say, forget about the fact that they have size. They're just point masses, and so if two point masses are together, they're still just a point. All right. So if they're stuck together, their center of mass is where each of them are, and so the center of mass moves at a constant velocity. Exclamation point. And for that reason, we can kind of do this to find a system's center of mass velocity at any instant. All right, what we're really doing is we're saying, here's where the center of mass, here's where the center of mass is. If we say that the velocity of the center of mass is the change in position of the center of mass per unit time, well, that's, let's see, sum of all these over the sum of all the m's. So that's just this. It's really a change in that. And then I divide by the t. Right? I can put the t down here. And this is the velocity. Well, sorry. Let me back that up. Yeah. So this part we can talk about the velocity of any part times the mass of any part. So that is the momentum of any part added up. And then we divide by our remaining net mass. So that's how we find center of mass of the system anytime we want. Notice, that's kind of like treating this thing as a hit and stick. Right? Here's all the initial momentums divided by all the masses. That gives us, okay, a final velocity of a hit and stick situation, but it's actually the same thing. Well, first of all, that velocity is the same velocity at any instant because the center of mass of a system experiences no change in momentum. All right, and that's a pretty profound statement. What we're saying here is that each part of the system during an interaction can experience a change in momentum because each object gets pushed on by the other one for a certain amount of time, but those pushes they exert on each other are equal and opposite, and they occur for the same amount of time, and so each of those changes in momentum, right, we can say that there's a delta p for each one equal to f delta t. But if there are two forces being applied to two different objects that are equal and opposite, and those forces are applied for the same amount of time, it means that the net delta p is 0, which is the same thing as saying this, that the center of mass moves at a constant velocity and or with constant momentum. Momentum is conserved. Fair enough? Okay. In a case like this, you know, post-collision velocity, that's another way of saying what's the center of mass's velocity. In a two-dimensional case like this, the way I would handle this is I would say, all right, there's always the same amount of momentum in each of two coordinate directions. So the net initial x momentum is 2mv. Should have done that in blue. The net, this should be initial. the net initial vertical y direction momentum is 3 mv. All right, so this system is always has to have momentum 2 mv this way and momentum 3 mv this way, and thus here is the system's net momentum at any instant, which is applying Pythagorean theorem, right? So that's 9 mv squared plus 4, well, 9 m squared v squared. Well, I'll just do that. So this is 9 m squared v squared plus 4 m squared v squared square root. Net p is 13 m squared v squared. Yeah? And if we want, right, then we can say, well, the velocity at the end is the net momentum divided by the net mass, or radical 13 mv over 5m. So at any and every instant, the system's center of mass is moving at, you know, typical radical 13/5. I'll say v. This is VCM. And this v is written in terms of these v's. That's what this v is. Okay, so what we found when we find this system's post-collision velocity is we've really found the net momentum at any instant. Or I should say, I guess if we're finding this is a net momentum, right, of our radical 13 mv. That's the system's momentum at any and every instant. This is the system's velocity, which is to say the center of mass velocity at any and every instant. Better. Okay. Now, yeah, why bother with this VCM? Well, it's a nice way to illustrate the constant nature of a system's velocity and/or momentum, but it can be useful in a special kind of problem. And that special kind of problem is when two objects collide. Well, I should say when they interact completely elastically. All right, completely elastically. Now. Let's run a little analysis of this situation. We've got two objects, two different masses, two different velocities, different directions. Initially, the net momentum is, well, let's see, we got 6 times 2, we got 12 kilogram meters per second right, and 8 kilogram meters per second left, hence I subtract. The net P initial of the system is 4 kilogram meters per second to the right. Right? Conservation of momentum says that this system's final momentum is going to be 4 kilogram meters per second to the right at some final instant, whenever that is. That could be, the final instant is typically after they collide, but it can be any time. All right? Now, let's look at the velocity of the center of mass. Remember, by definition, we do this. We add up all the momentums, we divide by the net mass. All right, so what we get is 4 kilogram meters per second to the right, I'll leave that as positive, divided by the net mass, 8 kilograms. And that is 0.5 meters per second right. Okay? Now, we're going to look at the velocity of each one of these objects. Notice the velocity of the 6 kilogram relative to the center of mass. All right? Here's the center of mass's velocity. The way you handle relative velocity questions like this is you could say, all right, V6 relative to the center of mass. Well, I have, this is this is V6 relative to what I'll call the lab. This is V4 relative to the lab. You might say relative to the Earth. I'm calling it from the lab frame. So this is, notice, the velocity of the center of mass relative to the lab frame. We're taking these velocities relative to a stationary observer, relative to the Earth, relative to the lab, something that's not moving. Well, at least is in what we call an inertial reference frame. So V of 6 relative to the center of mass. Typically we do this. That's V6 relative to something plus V something relative to the center of mass. Well, we can do lab and lab as our common frame of reference. Okay? Well, look, I have this. So I can turn this into V6 relative to the lab minus V center of mass relative to the lab. Okay? So V6 relative to the lab is this positive 2 meters per second. V center of mass relative to the lab is 0.5 meters per second, and it's positive, so minus 0.5 meters per second. So this is 1.5 meters per second to the right. Okay? And let's see, V2 relative to the center of mass, we'll do the same process, except I'll skip this preliminary step and say this is V2 relative to the lab minus V center of mass relative to the lab. All right, so that's negative 4 meters per second minus 0.5 meters per second. That's negative 4.5 meters per second. And what's neat about this is, look now, can you move by yourself? Oh boy. Bing, grabbing. Yeah, whatever. If we look at initial momentum and final momentum of the system from the frame of reference of the center of mass, look, we got a 6 kilogram moving that fast to the right. That's 9 kilogram meters per second to the right. Well, I should ditch that to the arrow. To the right, I'll just leave that as positive. And we've got a 2 kilogram at that velocity, minus 9 kilogram meters per second. So what we get is 0. So relative to the frame of reference of the center of mass, the system has no momentum. So what that's saying is that objects, in this case, prior to collision, are approaching the center of mass at the same relative speed. And we know, because momentum is conserved, that after these things collide, there has to be a constant amount of momentum. And we're just measuring from the frame of reference of, we're measuring from a different frame of reference, from something that's moving at a constant speed, just a different speed than our stationary lab frame. So you're probably saying, who the heck cares? Why am I bothering? Well, here's why. Okay, so we have our same scenarios before. The center of mass velocity we said is 0.5. Is this different? Or, yeah, it's still the same. Meters per second. Positive, meaning to the right. Okay. We said that this velocity of 6. Okay. Initially, from the center of mass frame, this thing is moving, we said, at a speed of 1.5 meters per second. Relative to the center of mass. This thing moving at a speed of 4.5 meters per second relative to the center of mass. Sure. Now, if these things interact completely elastically. I say collision in quotes because I should probably, do you have to qualify? No, you don't have to qualify. Elastic is one way. Collisions or interactions can happen in a number of ways, and this is, from a typical question phrasing sort of standpoint, you're going to see elastic, which means something very specific. You're going to see inelastic, which means a bunch of things, or completely inelastic, and that means hit and stick. Elastic means no, it actually means, well, the one big thing is that momentum is conserved. But that's the case for every single interaction. But the big one is that kinetic energy is conserved. And that's only if you see the word elastic. It means that no mechanical energy of the objects that are interacting can be converted into anything else. And what that means is they can't actually ever touch each other, because if they touch, there's going to be some increase in internal energy of little bits and pieces of the objects that are colliding. There's going to be some sound that is created as a function of losing some kinetic energy. So real elastic collisions, which can happen with charges that approach each other, or the same poles of a magnet sort of thing that approach each other, they can happen. It's just what really can't happen is objects can't touch. But there are elastic collisions. All right, so here's the deal. How do we conserve both momentum and kinetic energy? Well, here's a great thing about using the frame of reference of the center of mass. If this is the situation coming in, the only way coming out to have the same exact amount of momentum and the same amount of kinetic energy is if these two things turn around and move the other way at the same speed they came in at. So this object ends up doing this. This object ends up doing this. There's still, if you notice, now there's 9 units of momentum to the left. There's 9 units of momentum to the right. And if you were to find kinetic energy with 1/2 mv squared and 1/2 mv squared, well, we have the same exact numbers here and here, so you're still going to get the same exact amount of kinetic energy. And that's the only way to do it. If you take any two other numbers that might work to conserve kinetic energy, well, they're not going to work to conserve momentum. If you find any two other speeds or velocities that will conserve momentum, they're not going to conserve kinetic energy. This is the only way to do it. All right, so that tells us right off the rip, if we know what's happening prior to collision from the frame of reference of the center of mass, we know exactly what's happening after. The things just come out the way they came in the opposite direction. And now what we can do is we can transfer back to the lab frame, right? We know these two things. I don't know what this diagram is for, but we know this thing is now moving this way at what speed? 4.5. Oh, I know what this is for. So this is center of mass frame. 4.5 meters per second, negative 1.5, that's a 5 meters per second. What we can do is go back to the final velocity of the 6 kilogram mass in the lab frame of reference. So what I would do there is that's V6 relative to the CM, center of mass, plus V center of mass relative to the lab. Right? Here's our common frame of reference with which we can compare to other frames of reference. Okay, so this gives us, let's see, This gives us V6 relative to the center of mass is negative 1.5 meters per second. The center of mass relative to the lab was 0.5 meters per second, and that's negative 1.0 meters per second. I'm going to move that. I'm going to move this. So that's negative 1.0 meters per second. V final of 2 relative to center of mass is, or sorry, relative to lab, is, let's see, V2 relative to CM plus VCM relative to lab. There's our common frame. And this is 4.5 meters per second plus another 0.5 meters per second, and that's 5.0. So we now know, I mean, if we go back to the beginning of the problem, here's two objects with these initial momentums. What happens afterwards? I mean, we don't know how fast, we don't know in what direction for two different objects. That's a tricky problem, all right? But we can get to the answer by investigating via this center of mass reference frame. Okay, so we now know that at the end, this thing is moving this fast, 1.0 meters per second. This thing is moving this fast, 5.0 meters per second. And we can confirm that we're right because look at our net momentum in the end. All right, what we get is 10 to the right, 6 to the left. Right, so we get 10 kilogram meters per second minus 6 kilogram meters per second, and that's 4 kilogram meters per second. And remember, that's what it was before. Yep. Well, yep. And if we look originally, 6 at 2 and 2 at 4, we can look at the original initial kinetic energy, and we can look at the final kinetic energy, and those will come out the same. I'll do the finals right now. We get 1/2 of 6 times 1 squared. That's roughly 3. All right, plus 1/2 of 2 times 5 squared. That's roughly 25. So the net K in the end is 28 joules. Let's look at what it was in the beginning. We get 1/2 of 1/2 of 6 times 4. So that's 12 joules. And then here we get 1/2 of 2 times 16. That's 16 joules. Oh, we had 28 joules in the beginning, and we get 28 joules now. It means we have done this elastic collision correctly. Now, there are different ways to do this kind of problem. You can set up a different thing with a two equation, two unknowns sort of setup, and there's a little bit of an algebra trick you have to be aware of. What I like about this approach is that it forces us to use this practice of looking at things in different frames of reference and translating between one frame and another. It also allows us a pretty straightforward way of saying, we can jump from here to here before and after because it's the only way it can work. Okay, so what you should try is this one. Randomly made up these numbers, assume that this is a completely elastic collision. All right, there's a series of steps you got to go through. Here's the answer at the bottom. All right, other neat thing is you can do two-dimensional collisions like this too. I would highly recommend using vector notation and two-dimensional vector notation to represent velocity of center of mass. All right, I would not say it's this fast at this angle. I would say there's an I hat component and a j hat component. Okay? All right, folks. Farewell.